The electric rotary fan has always kept pace with the cooling needs of electronics products. It's also been the only fan technology since 1880. So, why do we need new fan technology today? The answer? It's being driven by a growing trend in the thermal management market. Market sectors like renewable energy, telecom, defense, and mobility are creating cooling fan requirements that are now beyond what rotary fans can deliver. These markets are cooling power electronics and other components in harsh outdoor conditions with systems that rely on rotary fans. They need fans that last the life of the thermal system, deliver higher fan performance at lower noise levels, and with reduced size and weight. But rotary fans have reached the top of their S-curve and cannot meet these conflicting requirements. Rotary fan bearings fail faster in outdoor conditions, where life expectancy decreases exponentially with temperature, which accelerates evaporation of bearing lubricants. Also, rotary fans must increase their speed in order to increase air performance, which results in more noise. When a product reaches the top of its S-curve, it has then reached the limit of its architecture's physics. To surpass those limits requires a new architecture. This is the problem NeoFan was founded to solve, and the compression fan was the resulting breakthrough. Next, let's take a look at the C-fan architecture and see what sets it apart. C-fans solved the premature failure problem by replacing rotary bearings with planar fan blades that pivot on infinite life springs. Air enters from the bottom of the fan and exits axially from the top. Air is forced through the fan primarily by centrifugal acceleration along the surface of the blade, and then leaves the blade at its tip. Higher pressures are synergistically created using the C-fan's mechanically reciprocating volume and a time-varying exit area. As shown in this CFD simulation, the reciprocating volume between the blades increases the pressure of the air as it passes through the fan. This is the primary reason that C-fans can provide much higher pressures than rotary fans for a given flow rate and operating frequency. As shown in this illustration, C-fans require a baffle to minimize the air backflow area during operation, similar to the frame of a rotary fan. The red shading shows the time-varying area through which the air exits the fan. The air volume flow rate generated by the blade approaches zero as the blade nears the maximum stroke point. Since exit velocity equals the volume flow rate divided by the exit area, the decreasing exit area helps to maintain the highest average air exit velocity during the cycle, making an additional contribution to the C-fan's pressure performance. Reciprocating volumes and time-varying exit areas are a first in fan technology. The C-fan's hybrid fluid dynamics delivers higher intrinsic pressures at much lower operating frequencies. As shown here, the primary sources of fan noise are blade tip velocity, blade pass frequency, and bearing noise. The C-fan has no bearing or mechanical noise and operates at significantly lower frequencies, resulting in higher performance with reduced noise levels. For more information on C-fans, contact Tim Lucas.